This video is for students in my Year 12 class for physics at St Augustine's High School, but if you are not in that class, you're welcome to watch it anyway. I'm going to go through lesson 10.1 from A-level physics from OCR, the Oxford textbook. For copyright reasons, I can't actually show you most of these pages on the video, but there's certain things I want to talk through and just give you the advice that I'd give you if it was a lesson. So I'm going to read through a lot of this and just check you understand some of the ideas and point out some different ways of thinking about things that I think can be helpful. So the first thing is that they do one good thing, which is to point out that you've already met Kirchoff's first law, because this whole section is about Kirchoff's second law. And you do know that Kirchoff's first law is that the sum of the current into a point in a circuit is equal to the sum of the currents out. And just remember, you can apply that to a point that has just one wire passing through it, or it can be a junction where there's multiple currents in and even multiple currents out, or together. More often though, it's going to be applied to branches. So you might have one wire coming in and two coming off of the same point, or two branches rejoining to return to a single wire. Now, Kirchoff's second law, we have looked at this already because I didn't want to just look at Kirchoff's first law when we first did it. But the way that Kirchoff's law is expressed in the textbook is to say that the sum of the EMFs and the sum of the potential differences is going to be 0. It's going to be equal. They're going to be equal to each other, so they're going to add up to 0. If you think of an EMF as a plus and a potential difference as a minus, that's a good way of thinking about it. EMF is into the circuit, PD is out. I think I already said to you the idea of thinking of PD as standing for potential drop instead of potential difference. Not quite the right way of thinking about it, but often quite helpful. Now, what else have we got? They then move on to talking about series circuits and parallel circuits. Now, I'm not a big fan of the phrase series circuit or parallel circuit. I'm not saying that they're wrong phrases, because you could think about a series circuit, a parallel circuit, and a complex circuit. But a better way to think about it when you're even first learning it is to think about the idea of a series arrangement or a parallel arrangement of certain components, because you can have a circuit with series sections and parallel sections. In a series circuit, things just come one after the other. Same if you're arranging them. One resistor with another wire leading to the next resistor is series. Parallel is when you have a branch and then the two resistors on two different branches, and that's not necessarily just an entire circuit arranged like that. It can just be part of it, so think of it as a parallel arrangement. Now, in a series circuit, what's going to happen is that if we apply Kirchoff's first law, you know that the current everywhere in a series circuit will be the same. So therefore it must be the potential difference, which is in inverted commas used up as you go around the circuit. Again, it's not quite the right scientific way of saying it, but for modeling it in your head, it's the best way to do so probably. What is actually happening is that the EMF is shared out rather than used up, is probably the right way of saying it, and that actually is what they say in the text, because I look at it now. So if you add up all the potential differences in a pure series circuit, they'll add up to the EMF. It occurs to me, I think we've discussed EMF as the voltage, if you like, although I hate that word, the voltage provided by the cell or battery or power pack, whatever you've got. Now, if you have two identical components, the potential difference will be shared out equally between them. If you have a component with a higher resistance, it will get a higher share proportionally with that increased resistance. You get a higher share proportionally of the potential difference as well. So that means if one thing has twice as much resistance as something else, it will use up twice as much of your potential difference, or get a twice as big a share of the potential difference. Now, Again, I'm not allowed to break copyright and show you the actual pages. That's why I'm fixing on just this little bit. A sample like this is covered under copyright law, but I want to talk about parallel circuits. So I'm now halfway down page 171. Now you know most of these ideas anyway, so I'll just recap them very briefly. You know that as the current divides up to go along different branches due to Kirchoff's first law, that current is going to have more current will go along the lower resistance path. So if you have a path which has double the resistance, the current will be half. So remembering that means there's a charge flowing along that path. It's not the current that's flowing, it's the charge that flows. The current is the flow. Now, when you get to a junction, the way to visualize it is the idea that half the electrons go one way and half the electrons go the other way, or a proportion go one way and a proportion go the other way, but each electron is still carrying just as much energy. And as I say, this is a way of thinking about it, not how it really is, but you can almost imagine it like each little electron's got a little meter reading how much energy it's carrying. And that's going to be the same for the ones that turn at the branch and the ones that carry on straight and so on. So don't think of it as the current changing in any way as it goes around the corner. It's kind of almost like delivery vans. If you have a bunch of delivery vans leaving a factory and they all have 100 loaves of bread in them when they leave the factory, just because some of them turn left to go to one supermarket and the others turn right to go to a different supermarket, it doesn't, taking a different route doesn't change how much energy they are carrying or loaves of bread they are carrying. It's not until they actually get somewhere to drop that energy off, or to drop their loaves of bread off at a supermarket or Tesco, Metro, whatever you like, that the actual amount of energy is going to change. Now, the textbook here does keep going on about different loops. It makes me nervous that you would fall into the trap of trying to analyze circuits in that way. Don't think of it. I try to avoid thinking of each loop as being a separate thing. I try to think of it as each branch being part of a whole. So if you have 3 branches, then they're really one component which is doing its job along 3 different sections, if you like. Now I'm going to turn to page 172 and just come off the textbook there so I don't break copyright. They do say here about the idea of considering each loop separately. I prefer you to think about each chunk separately. So if you look at figure 10, I'm thinking of mainly, rather than thinking about the 12 volt EMF, then 7 volts potential drop, then 5 volt potential drop, and then back to the circuit, back to the cell, I often think it's more convenient to think about the 12 volts EMF as a separate thing, the 7 volt resistor as a separate thing, and then the pair of 5 volt resistors as a separate component. I mean, one of the things you need to do a lot of the time is try and use both of those approaches, but to get locked into thinking them as a loop is going to be a problem. So you can think of those pair of 5 volt resistors as 1 2.5 volt resistor instead is often an equally good way of thinking about things. Now, using a combination of Kirchoff's first and second law, you should be able to answer all of the questions on pages 172 and 173. Rather than go through every single question and give you hints for each and every one of them, I think what I'll do is give you a chance to do those questions, email me with whichever ones you find most difficult, and I'll do another video to talk through any with which you have problems. It's most likely going to be question 4, 5 or 6 is my guess. I think hopefully question 1 and 2 and 3, I'm hoping you'll find them relatively straightforward. Good luck, and I'll try and get this video posted if I can get enough bandwidth to post it as soon as possible. And I'll get on to 10.2 as well. Good luck.